Alright guys, welcome to the first of magnetic fields. So today what we're going to go through is how to draw field lines or magnetic fields themselves in a straight wire, a loop, kind of a basic loop, and a solenoid, which is a series of loops. We're going to be talking about the magnetic force, and we're going to be discussing the application, which is the moving coil loudspeaker. So first of all, we have to get our head around some rules. And in this case here, we've got this thing called the right hand rule, RHR. Not the left hand rule, the right hand rule. Okay? Your thumb points in the direction of conventional current, that is plus to minus. We know that negative is the charge actually moves, so it should go negative to positive, but it doesn't. We're talking conventional currents, another one of these conventions. And it just works. Thumb, direction of conventional current, fingers in the magnetic field direction, and the force will actually come out of the palm of your hand. Alright? First of all, we're going to go through the right hand loop rule, which is the same kind of deal. Thumb in the direction of conventional current, and your fingers wrap around the wire. So that's the same, and the fingers will wrap around and show us the direction of the magnetic field. So in this case here, the first one, we have conventional current going straight up the wire. So if you imagine that wire like my texter here, I have my thumb pointing upwards because that's positive to negative, current's going upwards, my fingers wrap around it. So it's hard to draw 3D on a 2D thing, but it would kind of go that way, where on this side it's heading into the glass, and on this side it's heading out of the glass towards me. Okay, so it would loop around this way. Alright, it's probably almost impossible to see anyway. In this case here, the easiest way to do these is to pick a spot on that loop. Okay, so I'm going to pick a spot just here, and if I look at that spot just there, oops, my speaker's going to do some weird stuff in a sec. I might just do that, and I can hide there for a sec. I'm going to pick that spot just there. And if I imagine that spot just there, positive goes all the way over and down to negative. So at this point here, the current is actually flowing upwards, exactly the same as it was before. So at this point, my magnetic field is going to be into the board on this side. So into the board, into the board, into the board, into the board. This is where your hands are going to do weird stuff. So at the first point that I've just drawn, same deal, it's going to go into the board, out of the board. If I go to the top, so here, it's going to be going that way. So thumb is going to be coming under, and it's going to loop back towards me out of the board. And then here, if I have it downwards, same kind of deal. It's going to be looping into the glass on the inside and coming on the outside like that. So that's how that one would be drawn. Now, last one. This is almost impossible to kind of wrap your head around, because some people will see the field going one way and some will see it going a different way. But what I've got here is the current going into the board here, and then it comes out. So as it's spiraling, it's going, coming out of the board at the bottom into the board at the top. Okay, so now we're going to pick another point, and that other point that we're going to pick is, where can we do it? Let's say just here. So at that point just there, it's going orange now, at that point just there, the current is actually flowing, so it goes into the board, then it comes out of the board, but as it comes back towards me, it's kind of going like that. So it's really, really tricky to draw this one. What I'm going to do is say that the field is going into the loop, and it's coming around the outside. So this is far better doing a hands-on demo with an actual solenoid, but what we're going to end up happening here is the magnetic field is going in the center of our solenoid, into the board, and out of the board everywhere else. Alright, so what we're going to end up with is a whole bunch of field that goes that way, on the inside. So this is how we develop or build an electromagnet. Alright, and this electromagnet is, this is an electromagnet, this is an electromagnet, this is an electromagnet. It's just that we've got heaps more wires here, so we're binding the charges or the current closer together, which means that those field lines, the magnetic field lines, are able to bind and build on top of each other really close together. When they add together, we get something that's kind of meaningful and, strong enough to lift a friggin' car up in the air. Alright, so you can lift up a good couple 100 kilos with a C-cell battery about yay big. It won't last for long, but you can do it, just if you've got enough turns of wire inside your solenoid. Now the next couple of bits, the magnetic force. Magnetic force F equals BIL sine theta. That's a vector, that's a vector. Sine theta is generally going to be 1 because the angle will always be at right angles, generally at right angles. So sine theta will be 1 because sine of 90 is 1. So we're looking at magnetic field strength, B, current, I, and the length of the loop or the length of the piece of wire inside the field, delta L. So here, lots of delta L, here kind of a little bit, here bugger all. So that's why our force here is bigger, simply because of this. All right. So if we build up the force, we can increase the magnetic field strength, we can increase the current, we can increase the turns of wire. Now inside cheap car speakers, what they will do is ramp up the current by using less and less wire because copper's expensive, and little magnets or rubbish little magnets like here. If they use good quality magnets, lots of wire, then you don't need as much power to get as much force or to develop the amount of volume that you guys need or want. What that means is that you can have a big discrepancy between, you know, a 10-inch sub from one maker and a 10-inch sub from another, simply because of the quality of the parts that they're actually using or the sticker that they put on it. In this case, we're going to go back to our right hand rule for the force. The right hand rule says that our thumb goes in the direction of conventional current, our fingers point in the direction of the magnetic field, and our palm, out of our palm, is the direction the force would be applied. So I'm going to draw a magnetic field like this. The magnetic field is going into the board. This may not work as well as I'm thinking because I'm trying to work out where you guys are watching from, so this may actually be backwards. And I'm going to have a positive charge head that way. Now, according to my right hand rule, thumb in the direction of conventional current, the way the positive charge is going, so that's going to go to the right. My fingers are into the board because that's the way the magnetic field is, and the force is going to go up. So as this comes in, it's going to experience a force upwards, which is going to change its direction. It's not going to change the speed, all it's going to do is push it sideways. You may see where we're going here, and then it's going to go, you know, kind of across and up, so it's going to be going on a bit of an angle. So now we've got our thumb goes up on an angle, fingers into the board, and now the force is, you know, still at right angles to the direction that it's going. So the force will actually get, you know, that way. And you can kind of see, if I'll draw it down here, this thing will actually go in a perfect circle. This acts perpendicular to the motion of the charge that's moving, or the motion of the current, which is just a whole bunch of charges. All right, so the last part, the permanent magnet, the coil, and the cone, speaker cone for the moving coil, guess what, it moves, loudspeaker. We have permanent magnet supplies a magnetic field. So we have a magnetic field from the magnets. That's pretty groundbreaking, isn't it? We have a speaker cone which moves air. Moving air is noise. And we have a coil which is a solenoid, just like this one up the top here, which means that it's going to produce a force going this way. Guess what? If I swap these over, the force will go the other way. So now I've got a magnetic field, north and south, so north here, south here, north here. We've got a magnetic field set up kind of like this, but the other, like horizontally instead of into or out of the board. And what we're going to do is get our magnetic field to interact with the coil, the solenoid, which has a current flowing through it, and what's going to happen is we'll make the current go one direction. So if we have our magnetic field going like this, actually, how am I going to do this? If we have a magnetic field going in one specific direction, what will happen is our coil, the current in the coil, will actually interact, and the force due to the coil and the magnetic field will be upwards in this case. If I then reverse the current in this coil, it will actually produce a force that's downwards. So if I can flick this current positive, negative, positive, negative, positive, negative, say 30 times a second, so at a rate of 30 hertz, that will make the speaker cone go up, down, 30 times per second, and that's going to play a note of 30 hertz, really super deep sub noise. Okay, if I make it go at 2000 hertz, so the frequency goes up and down 2000 times a second, that's going to play a note of 2000 hertz, which is a little bit more high pitched, quite a lot more high pitched. If we're in the several hundreds, that's where several hundred hertz, few hundred, 600, whatever, that's where most of the music is actually going to live. So you have a huge big sub, which will move nice and slow because it's big, it's heavy, it takes a lot of effort. Remember, F is also still MA, so to move that mass, to accelerate that mass up and down, takes a fair bit of effort, and this is the force that's providing it, so you can't really get it to go up really fast, down really fast, so you can't switch it that quick. If you get smaller, so mid-range speakers, they'll move up and down a lot faster because they're a lot smaller, and then if you get tiny little tweeters, they'll go up and down thousands of times per second based on whatever's going on here. So your head unit or your amp will actually talk to the speakers, and they'll tell them how fast to switch positive, negative, positive, negative, positive, negative, positive, negative, for the speaker cone to be forced up and down due to this guy just here. Alright, I will show you a couple of real life versions of this in the lab in the next few days or in the coming weeks, simply because it's a lot easier to spot it in person than from my not very great drawings. See you next time.